So welcome to this lecture on thermochemistry. This is your second lecture. Here we will be calculating delta H naught reaction for any reaction. Okay. So the whole idea and the goal of thermochemistry is that you should be able to predict delta H reaction for any reaction, whether it can be calculated or carried out in a laboratory condition. You should be able to predict. That's the whole idea behind thermochemistry. Okay, here, so we'll take up a very small example. Let us take combustion of methane. So you have your CH4 methane. It's a gas temperature at a given temperature, and 1 bar pressure plus 2 oxygen, gas temperature, and 1 bar pressure. So this is going to give you carbon dioxide, gas temperature, and 1 bar, plus it's going to give 2 water molecules, which is liquid temperature, 1 bar. Right. So this is your combustion reaction. Now, how do we calculate the delta H naught reaction for this? So first, what we do, we decompose reactants into elements. Step 1, decompose into their respective elements. Now, how do we form methane? So methane, if we decompose, now this comes from this graphite, the most stable form of carbon, which is a solid, temperature 1 bar, plus now 2H2, which is gaseous, temperature and 1 bar. Okay. So you have decomposed the reactants into elements. Now, if I call this as delta H1, okay. So this is what reverse of formation of methane, and therefore the enthalpy change for this will be equal to delta H formation, and this is at standard state of 1 bar, and CH4 gas. Okay, this is your first. No, this is what we do. Now, is there another reactant? Yes, of course, there is oxygen. So how do we decompose oxygen? Nothing. 2 oxygen, gas temperature 1 bar. It can be decomposed to oxygen itself. Nothing complicated about that. Oxygen is the most stable form. So this is pretty simple. Now what is this? I call it this one. This is your delta A formation. Okay, and now we know that the enthalpy of element in its most stable form at 298.15 Kelvin and 1 bar pressure is 0, right? So this will take. Now, did I forget to mention that the temperature we are considering here is 298.15 Kelvin. Now, what is the second step? Second step is put elements together to form products. Products. Okay, now what is the product that we are looking here? One is CO2, carbon dioxide, and water. Let us see how we can get both of them. Now, carbon dioxide is graphite, solid temperature. Okay, this is your delta H. Okay, and what is it? This is formation of carbon dioxide. Now, is there another product that we need to form? Yes. So water, we need water, right? Okay. So this is H2 gas temperature bar plus water heat temperature bar. Okay. Now, actually, it is not H2O. It is 2 times H2O. So this delta H4 is not just formation of water. Okay, it is twice the formation of water. Fine. Okay, so if we put all of them together, now what is the third step? Third step is we have to use Hess's law of constant heat summation. Okay, so what is this first thing? It uses the fact that enthalpy is a state function. Okay, second, its statement form it is. So because enthalpy is a state function, it can be added. We can add delta H's around any paths. We can add delta H's around any paths. Okay, the statement, if you have to note, it is, I'll give both the statements, you can write any of this. The standard reaction enthalpy is the sum of values for the reactions into which if the overall reaction may be divided. Or if you want another statement, you can take it as the heat absorbed or evolved in a given chemical reaction in a given chemical equation is the same whether the process occurs in one step or several steps. Okay, we'll discuss more about this Hess's law and its consequence in another video. For now, we'll stick to this, and what we need to know from this is, now since H is a state function, first you have broken down all the reactants to their elements, and then you have combined these elements to form products. So you're going from reactants to products. However, you have broken down into now as many steps as possible. You break them. The fact remains that H is a state function, and therefore you can add all of them together to get your delta H reaction. As simple as that. So your delta H reaction will be equal to, for this particular, will be equal to 2 formation of water plus H naught formation of carbon dioxide minus, okay, this is delta H formation delta H formation of CH4. Okay, this will be your delta H reaction. So in general, for this particular reaction, right? See, what we are doing is, if I have to put it diagrammatically, you have your reactants forming products. Okay, so what you do first, you break down the reactants into their elements. In their standard state. Okay, so first what did you do? You have to take them apart. And then here you need to put them together. Where you will get delta H will be the formation of products. Okay, so as simple as that. Let me give you a everyday example, okay, for you to understand this concept. Now you have, let us see, this is a very imaginary but relatable reaction. You have tea and then you want to react it with a coffee powder. Okay, so supposing your products are coffee plus tea powder. Okay, so now what, according to this calculating enthalpy of reaction, what you should do, you should first break down the reactants. So how do you break down the reactants? First break them into, okay, what did you add first of all in the first, in tea you added milk was there, good, water, okay, then tea powder and sugar, right? Okay, now coffee powder in its stable standard state is coffee powder again. Okay, now these will react, except now tea powder, what will happen, milk, water, sugar and coffee powder will react to give you coffee. Okay, so you have broken down, take them apart and then put them together. Okay, and for any reaction, in general, delta H reaction will be equal to H formation of reactants. So where mu I is stoichiometric coefficient of species I. Okay, so this is your standard reaction enthalpy. Okay, so shall we solve one small problem? Okay. Calculate the standard enthalpy of the reaction. It looks very simple here. You just need to put, be able to understand catch few points here in thermochemistry. The concept, everything is taught till first law of thermodynamics. Here it's just application part. So calculate the standard enthalpy of the reaction. So what is given? Given delta H formation of zinc oxide solid is minus kilojoules per mole. Okay. So how do we calculate the standard enthalpy of this particular reaction? Nothing, very simple. You have your delta reaction is given by, what is the product? Formation of zinc solid plus, what is the general reaction? Plus if you have to, reactants, right? Okay, so in this particular reaction, your seems like all the stoichiometric coefficients are unity 1, and therefore it will be delta F formation of ZnS plus delta F formation, okay. So and what is the enthalpy of formation of zinc? Zinc itself is in its most stable form, so it is 0, and for carbon dioxide it is minus 393.51. What is the enthalpy of formation of zinc oxide? It is minus 348.28, and enthalpy of formation of carbon monoxide is 110.53. So if you calculate, so put the answer. So please send your answers in the comment box, comment section. Let me know whether you have watched the video till here or you're gayab in between. Okay, so this was your video on calculating enthalpy of reaction. So next will be Hess's law. So thank you so much. See you. Bye bye.